Okay. The plan today, by the way, I have a problem with my screen. There is some hardware problem on my laptop so I can't see the whole screen. So if I kept my slides in this fashion, is it hard for you to read? Is it okay? Rather than go to the full screen mode, in which case I won't be able to see parts of the slides as I speak. And that kind of sometimes throws me off when I try to make it bigger. Is this okay?
Yeah, it's okay.
Okay, so I was planning to have, let me call Diganta because I wanted to have a short lecture, maybe for half an hour at most today, and have Diganta review the code. Hopefully he will show up. So let me start. What I want to do is mainly show, I added some comments based on some questions and remarks in the last thing. So I just want to quickly go through those comments that I've added. So that way you can refresh your, what the points I covered in the last class. Last class in constructing an abstract transformer for some components of a programming language. Okay, so okay, all these things are. I mean, as I go through, if you have any question, you can stop me. And this is just a recap of what collecting semantics on concrete domain is. So this is where I added one comment to emphasize the question good question that Dhruv actually raised, which was, why not? Why construct an abstract transformer? Why can't we just do this one? Because the abstract transformer is defined by this condition, alpha post of things. So for any given abstract, you can actually apply the gamma, then apply the post and alpha. So this is expensive, especially because both alpha and gamma, they don't have to be computable because on infinite sets. And as you know, post on infinite sets and post image computation function has an existential quantifier. Eliminating that on infinite domains can even be undecidable. Even when it is decidable, it can be not very efficient to compute. And that's the reason that we want to construct a definition for a post hash. That's what I call as the abstract transformer for the post, directly in terms of the parameters defining the abstract element. So it is an over approximation of post. That is one point. And this is something maybe I kind of rushed through. So the abstract transformers, of course, we'll be using all these things, okay, both meet and join in, defining in constructing the abstract transformer, and sometimes even this check of whether two elements are in the abstract domain are related by the partial order may also be need to be computed. Now, I kind of rushed through, so I just wanted to see the reason that this one looks complicated is because, after all, a meet is supposed to return the largest interval that is contained in both x hash and y hash. But since x hash and y hash, they are interval domain, but they may have multiple variables, so they are vectors. Okay, each variable has an interval domain associated with it, with its own lower and upper bound, and that's why this looks this definition is over vectors, okay, of computing the mean. So this is supposed to return the largest interval for each variable that is contained both. That is contained. Yes, I mean the smallest, I should say. Oh no, the meat, it does indeed return the largest interval that is contained both in. Oh. Is there a question? Let's see, is Diganta here? Still, so don't see Diganta. Okay, so I'll call him when I finish up. Yeah, and if any one of them, see, tau is, it's actually a vector, okay? One bound for each of the variables in it. So if any one of them is at bottom, that is the empty interval, then you can return the whole thing to be bottom, because this is, so this, it is supposed to, it's a conjunction, okay? It has to satisfy all of those constraints. Otherwise, it will, compute the largest interval that is, contained in both X hash and Y hash by, taking the max of Lx and Ly and min of Ui for each of the element, variable element. I mean, the domain that is for the variable in the vector. That's why this looks a bit complicated. A join is similarly supposed to return the smallest interval that contains both its arguments. Okay? So that's why if any one of them is a bottom, then it returns the other one. Otherwise, it has to just compute the min of Lx and Ly and max of Ux and Ui for each of the elements. Okay, for each of the variables in the vector. That's why this looks complicated. Okay. Any questions here?
So in the third point, what does the vector inverse notation mean?
Oh, it's just, I mean, a column vector. I mean, I couldn't fit the thing. So, I mean, I'm representing the various intervals for each of the variables as a vector, okay? As a column vector, that's all. So, in all my examples, the first, row in the column vector is the interval that defines for x1, the first variable, the second variable, and so on. Okay.
Yeah.
Just a column vector. That's all. So this bottom here is actually a vector with all of them being bottom. That's what each of the components being.
And bottom corresponds to the empty interval, right? The empty set.
Yeah, the empty it's the empty set, and usually it's denoted by plus infinity, minus infinity. I mean, yeah. So with the lower bound. Okay. Any comments? I don't think I have any comments here. So this just defines alpha and gamma unique way in a given Galois connection. And as we said, we define the post as the post hash as an over approximation to post. The best, that's the most precise abstract transform is one which equates, which is exactly equal as a function to this function, but we can choose any abstractions. Okay, and we find a sweet spot. Okay, when you implement abstract transformers for various operations and so on, you make trade-offs, okay, to get you know, trading off efficiency for precision. Okay, so this is just a language, programming language that we introduced, and that, and as we will see later on in an example, we will have a CFG representation for these things, and that's why in which we have nodes representing locations and edges labeled with one of these three basic commands to represent our program. And then we saw all these concrete statements for each of those concrete semantics. That's the mainly this is defining for each. And then the post operator, we have to define the abstract transformer corresponding to that, and that's what we were doing here. Okay. So once we define, so pretty much the only comment I have here is, so the exercise of defining an abstract transformer for all the constructs, expressions, constructs in a programming language consists of defining for an abstract transformer for every operation that is from which expressions in the language are constructed, and for each of the constructs starting from the basic commands. Okay, so that's what we'll have to do in such a way that the abstract transformer is an over-approximation of its corresponding concrete version, and it has to be defined directly in terms of the parameters that define an abstract element, which for the interval domain is the lower and upper bound. The guards are, a little bit of a, kind of a mystery or a puzzle. So because they are, Boolean function, that is predicates over sets of states. And what you really want to represent them, the semantics for them, is actually, you need to return the subset of elements when you apply a guard to a set of states. You want it to return that semantics to return the set of states, exactly those sets, set of states, subset of states of X, which makes this predicate true, which is, which is really, if you were doing in concrete semantics with predicates, is just applying just the predicate itself defines that set. Now here we'll have to define, okay, its abstract version. We'll have to define such that given an abstraction of the concrete set X as X hash, okay, we'll have to define the result of applying that predicate to that abstract domain. And it has to be this is what is the defining criteria, that it takes the meat, okay, of these of X hash and the alpha, or an over approximation of that concrete set of a set of concrete elements that make which returns true when evaluated, when that element is evaluated for the Boolean predicate G. Okay, so we already saw this, this example. Now, if my guard, the predicate defining the guard, it's kind of is itself fits conveniently within the predicate defining the interval domain, then you can get that set for which this thing is, true, for which this predicate is true in a precise fashion. Okay, if x is less than or equal to 10, then you can, that interval is represented by from minus infinity to 10 by the two parameters minus infinity and 10. Where you will potentially lose precision is when you have something like this, for example. Okay, so here even conjunction of interval constraints are okay, but when you have disjunctions, etc., then you will have to in order to compute them directly, you will have to do this kind of operation. For each of them, you will compute the corresponding interval. Because in this form, each atomic formula here can be represented by an interval domain. So by computing the smallest set that includes this set of concrete elements, and then you will have to use meet and join. So whenever you use join, for example, here you will lose precision. Okay, when you compute this and then this part of the thing, and then you use a join because it's a disjunction. So disjunction corresponds to using the join. Then you will lose some precision. Okay, so that is one source of loss of where you lose precision when you apply the GAN. Okay, and the GANs, as you know, will be used inside as part of if-then-else statement. So that's why you'll have to apply whatever the domain that represents the state prior to the if-then-else statement. Then you have to pass it through the guard, get a new domain like this, as shown here, and which is what will then be used to evaluate the two arms of the statements in the two arms of if-then-else. Okay, so that's where you will need this. Okay, that's what is illustrated here. So I've just added an example here as to where this join. So whenever you have an if-then-else, then there'll be a join also after join of the two domains that you get after propagating the abstract domain across the two arms of the if-then-else. So for example, if you start out with an interval, initial interval for the variables as 2, comma 15 as one variable here in that vector, which is x. Okay, and then you have the guard say x is less than or equal to 10, which is the guard that is used as the condition in the if-then-else statement. Then you'll have to first get that subset of the interval domain, the input interval domain, for which x is less than or equal to 10 is true, and that's where you will apply. Okay, these are the two things. Okay, for the then part, you will get 2 to 10. Okay, because that's what you have to take the meat of 2 and 15 and those values for which and the interval that is characterized by this x is less than 10. So you will get 2, comma 10, and the other the negation of that guard, which represents x greater than 10. You will similarly propagate the the domain 2 to 15 across that guard. 11, 15. After that, so that part is clear. Now, after that, you have to apply whatever. That's what x01 hash and x02 hash will be, and then you will apply whatever the statement S1. In this case, x is equal to 1 and x is equal to -1. So when you do that, then what you will get is -1 and 1. Then you will take the join here of the two things, which is what you will get. As you can see.
আমার ব্যাগ
Yeah, can I request the person who's, having some background noise to mute? Uh,
Yeah, I texted Sudakshina, but I think
Yeah, it was due to me, sir. Sorry.
yeah, so as you can see here, there is some potential loss of information, not in this case, but as a result of propagating the domain across the guard. When we take the union, there is also loss of information. Okay, so here, because you have to take the join of those two things, 0 is actually not a reachable value, but it gets included in the union interval. So there are two sources of imprecision. So that's how these things get propagated across if then else conditional statements. Any questions here? Okay, I also want to take the example of a relational operator. So in this case, there was only one thing. I mean, it was only one, the guard was defined over a single variable. Let's suppose that we have something like this, where the guard is a predicate over, say, two variables, x less than or equal to y. So here we will have a vector. The first interval denoting the current value in the abstract, the current interval over which for x, and ly uy giving the interval that captures the current set of values in the abstract domain for y. So the question is, what should this be? So here, this is something that is not directly represented. So this is kind of a relational operator. Okay. So what do you think should be in? Okay, whatever that you return has to be as some interval. Okay. So you should extract as interval. It can be an over approximation. That for which some subset of intervals for each of these variables x and y that the variables can range over, for which that should include there should be an over approximation of all the values for which the pair x and y will be true. That's how you will have to define it. Okay. Of course, you could include the whole thing, okay? So there'll be some values of x and some values of y for which this will be true. Of course, you could pass along the entire interval, okay? Because which is certainly an over approximation. So what this has is, this is the current value as intervals for the variables values for x and y, from which we have to remove the set of values for which this is false. Okay, and that's how this thing is is defined. Okay, so so you could say that. So, but you could do better than this. Okay, of course you could, you can pass on the whole thing, which will certainly include both. That will be a very coarse over approximation. Or you can do this. Okay, you do a bit further analysis, for which, if you know that there are certain regions of these two intervals for x and y, for which it is, depending upon what Lx and these upper and lower bounds are, if suppose Lx, the two intervals that gets passed on to the abstract transformer that we are trying to define for this guard is such that, Lx is greater than y, then there is no overlapping region at all, right? Between the region for which the guard is true and you're starting LX. And then for that, you can then just return the empty thing, and then you can, otherwise you can return the whole thing. That is a slightly better approximation, slightly better in the sense more precise than what is done here. Or you could do something, even better by kind of doing more analysis on the lower and upper bound. Okay, so this situation depending upon the overlapping regions. So what I did just now, what I showed just now, was that it was precise, at least for those cases for which there's no overlap at all. There's no overlap, and and there can never be. There's no region. The region for which x less than or equal to y is true is empty. Okay, and therefore in those cases this would be give a better approximation. So you could do the same thing, and ideally what you can do is to exactly capture that region, the overlapping region, for which you know that all the pairs of x and y, for which that will be, for which this x less than or equal to y will be true, will be that overlapping region. And therefore, what you can do is you can define that, okay, as actually the meet of these two, these two intervals. Okay, so this is how you do. Of course, this overlapping region, even within this overlapping region, which is captured precisely by this using the meet operation, still there might be some components there for which the x less than or equal to y is false. But you can't do anything better than that, okay? Because you will lose some information when you represent the values that x and y range over as intervals. So this is the kind of analysis that you will have to do, and then define your abstract transformers as a function of Lx. I mean, these what I call as parameters for the abstract domain. Okay, and then you have to apply them for a particular domain that you have at when you propagate these domains through your program. Okay, and that's how you will define. And of course, you can you have to do this analysis to get the most precise that is possible. Trading off, keeping in mind how efficient it is to compute that. Okay. Any questions here? Yeah. So building an abstract transformer, an abstract interpreter for programming language will consist of a big part of it is building the abstract transformer for all the components. And that's what I'm illustrating now. Okay, so you already saw doing guards and how you could do if then else. So we'll come to the next part of how do you propagate across a program which has loops. Okay. So here I'm going to show you for a simple program represented as where the loop, represented as a CFG. Okay. So this program initializes X as a single program variable X. Start with some initial set of states, which is characterized by the domain, abstract domain, and the interval domain denoted by X naught hash. Then you initialize X to 0. This is the location at the head. Then you keep you keep incrementing X by 1 as long as X is less than 5, and you exit the loop when X is greater than or equal to 5 to get to the exit point exit location of its 4. So obviously, when you have a loop-free straight line programs, you could propagate the intervals as I had, as I showed, using all the abstract, composing the abstract transformers and doing joints for everything else and so on. But what do you do when you have loops? How do you, propagate the thing? So as the name here indicates, that you will have to compute a fixed point, okay, for the loop in order to get the least fixed point representing the invariant, okay, that you can derive, the least, the tightest invariant that you can derive, the strongest invariant that you can derive in the abstract domain at that location, okay? So, and I mean, there is an advantage in representing, in developing how this is done in terms of CFG, because there, you can have multiple loops nested in whatever way that you want, okay? And this infrastructure, this mechanism that I'm going to show you, it applies. It's easily applicable to all kinds of loops that have different kinds of shape. Okay, so the goal here is to derive the least fixed, point that you can compute at each of these locations. Okay, so to begin with, I'll assume that x can be anything. So the initial domain for x is top, which really corresponds to true, which means that it can hold any value from -infinity to +infinity. So what happens after you do x, the first initial assignment? What will x1 hash be? Anyone?
The interval 0, 0.
Yeah, so that is represented by, actually, you're right. So, but we will represent. Okay, so you will have to apply whatever the abstract transformer for that assignment statement is to x hash. So you're right, that will be 0, 0. But what we will do here is to get the defining, the equation that defines the propagated domain value at each of these locations. Okay. Now at x1, yes, what you just now said, okay, is that someone said it's 0, 0. It is true. But the only way that you can get to x1, I mean, the only value that you can propagate to x1 hash is is by this transition. When you have a loop, that is actually not the case. Okay, you can also get to this location x1 used by this package. Okay, starting from x3 hash. Okay, but we don't yet know what exactly is the best propagated interval value is, but we can do that as an equation. Okay, so this should be the merge, that is the join, whatever is the value this location that you can associate with x1 hash is defined, has to be is defined by this equation. Okay, this is actually a it's kind of a simultaneous. You will see that it is a recursive equational system. Okay, so it's simultaneous equation. So it is something that whatever you get after propagating x0 hash across this statement x assigned to 0, and whatever that you get by taking a join of that with whatever that you have for x3. Okay, but we will get to x3. Okay, as to what that thing is. Given this thing, then you know that in order to what is the value, the propagated domain value at x integral domain value in x2 hash is given by applying the guard, okay, which is by the guard in the which is the which corresponds to the transition here, and then that's what x2 is, okay. And after that, you propagate x2. What x3 will be, because that's the only way that x3 is through that edge from x2 to x3. So this equation captures exactly what the value at x3 is. Okay. Now x4, the only way you can get to x4 is by making the transition, the exit transition. That can be defined in terms of x1 hash. Okay, which is just propagating it, the whatever the domain value that you can, the best domain value that you can compute at x1 hash across this this guard. So what I'm saying is the least you have to compute. So my solution for the entire system is solving this set of the least solution to this set of fixed point equations. Okay, I call them fixed point equations because there is, you see here, there is circularity here in this equation. X1 is defined in terms of x3, and x3 is and x2 itself is defined of x1, x3 is defined in terms of x2. So there is interdependency between these two things. That's where you will need to propagate. Okay, you need to compute the fixed point, okay, across multiple locations here simultaneously to arrive at the least solutions for all these locations. Okay, and so whatever is the least solution that can simultaneously satisfy these set of fixed point equations is your in your abstract domain. The least solution is the best set of invariants for all the locations that you can actually get. Okay, so what I've set up is I've defined the problem. Okay, this is a solution, least solution for a set of fixed point equations. So the question is, how do you compute this solution? We already saw, kind of, if there's only one loop and there's one entry, one exit, you could take the transition function of the body, and then you could kind of, compute the iteration. So something similar to that is what we'll be doing here. But it will be, you'll be extending that, basically we'll be using clean iteration. Okay? The clean iteration, the way it was, the theorem that we saw was stated was for a single function, okay, for a single equation, you could say, of the kind x is equal to f of x, okay, LFP of s. So this theorem, you could use the clean iteration by iterating over x to solve, to come up with the least solution to a single equation, okay. Whereas what we have here is a set of equations that need to be solved, and a clean iteration theorem can be generalized to a set of fixed point equations. Okay? And we're going to see how that can be done by means of showing you an algorithm, okay, for that thing. So you could say that given a fixed point equation system as as was defined for a set of as a set of equations for where with one equation for each location, you could, if that can be represented, so there's a set of locations. Okay, so for each location you already saw that there was one equation with an f naught. It was defined, f naught, which could in general take any one of those domains associated with any one of those locations. So this is the kind of equations that a set of equations that you have. With each equation, for each equation, there is a f naught, just like there was an f here for this equation. Okay, and what you'll have to do is you will have to kind of do clean iteration over all these locations. Okay, starting from bottom. Okay, so because if you had only one equation, you would start with bottom, and then you would repeatedly apply F naught, right? Computing the ascending chain until you reach the fixed point, until you're no longer adding anything. Okay, and that's what you will do, but you will have to do here for taking into account all the locations simultaneously. And so we'll first initialize the domain for every location to bottom, and W is the set of locations that you have. Keep that in a set, and you will arbitrarily choose one location, okay, from the set of locations. You have, and then you apply the function FL corresponding to the equation associated with that location once. Okay, and I mean you can choose this arbitrarily. Okay, you pick arbitrarily one, and then you propagate the domain by applying the FL corresponding to that. And if what you get, so when you apply that, you will get a new domain. That's what is denoted by XL hash prime. If that is, you still have not reached a fixed point at that location, that is, if XL hash prime is still greater than XL, that the value that you already have at that location, then you have not reached a fixed point for that location. Then you put back that you removed here. If you're not, then you'll have to propagate it further. Okay, and you may be able to improve it further. So you will put back that location, and then you keep doing this as long as you will terminate it only when all the equations, all the locations reach fixed points, and when that happens, you would have removed every location from your work list of locations, and you would terminate. This is how. This is kind of doing clean iteration simultaneously over a set of fixed point equations. Okay, using the function corresponding to each of those locations. Yeah. So let me take an example.
Sir, can you go to the previous slide? Yeah. So
this one or the one before?
The next one.
The next one, the before.
The next slide, work list algorithm.
Okay.
Yeah. So in the third line of the while loop, what does that set mean? The set of L prime such that L comma L prime is in E.
So this one is you would have removed W there. Okay. So what this means is you will have to put back. So you will have to put back, okay, from there. So you will have to put back all the locations. Yeah, see all the locations. So you would have, you are, see, from each of those, you have removed one location, right? So from that location, you can have multiple things, okay? From here, for example, there is two outgoing edges, yeah? One here, yeah?
Yes.
So you will have a choice, okay? When you, which one you will pick, okay? And then if you pick this, then you will have to, and that's what, all these outgoing edges, okay? You will have to, all the target locations of the outgoing edges from L, okay, will have to be put back, okay? The same.
We are just removing the location L from the set
Yeah,
W, right?
yeah, you're removing the location from L, but then checking if the new XL prime that you get by propagating, doing one more clean iteration by applying the FL for that, if
Yes.
that is contained, which is the negation of this, okay, then you reach fixed point. Then you do not put anything, okay?
Yeah, I'm just saying like, shouldn't we just do W is equal to W union singleton set L? Because the only location that we are removing is L.
Yeah, but what you're doing is, after doing this, you're removing L. But what you'll have to put back is you have to put back the edges, okay? I mean, you have to put back the outgoing the destinations of those nodes, but they're already there, isn't it? Yeah.
Yeah.
Correct. Yeah.
So basically, when we change Excel, everything that will change because of that have to be added back, right?
Correct. Yeah.
But that's all. But all of the others are already there in W.
Those are already there. So that's right. So you're right.
Not necessarily. We might have removed them in a previous iteration.
Yeah, you could have removed them. So let's see an example, okay? And it'll be.
Oh, I think yeah.
You could remove them, so therefore you will have to.
Right.
Yeah.
And in particular, L comma L is an edge, right? From any location to itself is also counted as an edge.
No, but that is counted an edge if that edge is there. That is not necessarily there. There's no self thing here. Okay. So, for example, here, if you pick to this location to apply the F1, then you might have removed this because you propagated this something else. But since something changed here, okay, you will have to put back all the locations. This itself will get put back only if you come back in there. Okay, you're not putting L in this step automatically. You're only actually correct. You're putting only all the target edges. Okay, you will remove this. Okay, at this time, but you will put back on. You will put all the target edges, and then at each point you're computing the you're propagating you're computing the strongest propagation across that edge. Okay, and therefore you will this will you've already computed this as a result of, because this has changed in this iteration, you have to now try and see if this can affect other things, okay, on which other locations that are dependent for their values on X1, which in this case is X3 and X4. And they might have gotten removed, and therefore you will have to put them back.
Yeah.
Okay.
Yeah.
And you will put back X1 only, because X1 may end up getting, you've removed it in this iteration. It will get put back only when, since you have put X3 back, and then there is an edge from X3 to X1 will come back. Okay. Eventually, if there is a back edge to a location. Yeah.
Yes.
Okay, that's what is happening. Yeah, that's a good point. Yes. So it's not, you're removing it in here and you're adding only the target edges. Okay, there are multiple edges, like it can happen in the case you have either non-determinism or you have these loops. Okay. Yeah. So the question is, here the algorithm is expressed, in such a way that you can pick the next location to pick from the work list of location can be arbitrary. Okay, that's the way it is defined. but the question is, how do you choose L such that this was to guarantee that this will terminate? Okay. Yeah, I mean, you could actually, as long as you don't ignore any equation indefinitely, okay, you can pick, as long as you don't ignore it indefinitely, then you can pick any location that you want. Okay, yeah, as long as you are fair in not ignoring any location, or you can use some topological ordering, okay, of the nodes after removing all the back edges. You get a directed acyclic graph of your program by removing the back edges that make loops, and then you can pick topological ordering. Okay, but then there are different iterations, I mean strategies that you can actually use to get a convergence, faster. Okay. So there can be other strategies. So let me, quickly show this example. That, yeah, I mean, how that is propagated. Okay. So you start with bottom. Okay, now I think this one is not good, so I'll go to the next one. Okay, so you have this one. So when you start out here, of course, if you picked, okay, this is the order in which I picked, but it does. If you picked anything other than 0, obviously there is no improvement at all. Correct? Suppose I picked equation one of either 1, 2, 3, or 4. Do I make any progress at all? I mean, 1 you will make a progress. Okay? I mean, yeah. I mean, if I picked 0 to propagate, then I'll make a progress. Okay. So if I picked, yeah, if I picked location 1, I will make a if I propagate 0, then I'll because if I picked any one of these, like 2, 3, 4, etc., since x0 is already, I mean, x1 is bottom, and if I apply the f0 corresponding, if I propagate that x1 hash across this guard, I will only get bottom. Okay. Therefore, the only way you can make progress is by picking x0 and propagating it across. Actually, by picking x1 and then propagating it across this one. So that is what maybe I'll go into this thing. Okay, if you pick location 1, then you will improve. What happened? Yeah. So okay. So you will. Yeah. You picking 0, you propagate to 1, and that will give you 0, 0. Okay. So that is the first thing that you do. And after that, you can pick 1. First you pick 0, propagate, you get, you improve what is there in 1 from bottom to 0, 0. Okay. After that, you can pick in that order. Sorry. So you can pick in that order like I've shown here. Okay, this order, and then you will improve. 3 will be improved to 1, 1, isn't it? Okay. This will be improved to 1, 1. Okay. Eventually you'll get 1, 5, but you will get 1, 1, and then nothing else will improve. So other than 1 again. Okay, in which you will take a join of 1, 1 and 0, 0 to improve the domain here to 0, 1. Okay, so that's what is happening. Okay, after that you kind of you repeat that. Okay, and do that. And the reason that if you picked a chaotic ordering where you pick randomly, you should at least give those locations which when picked will advance, will make some progress, a chance, okay? So that you will be making overall progress, and that's all. That's or if you capture the dependency on this among these locations in terms of this kind of an ordering, then you can use that linear ordering to choose your location. Okay? The next location to pick to apply the cleaning iteration for, and that's how you could you can do. So, and when you do that after 5 iterations, you will end up getting all the locations, the domains that you get at all the locations will saturate, okay, with fixed points, and you will not be, and they'll all the locations will get removed from the working list, and you will terminate. Okay, so that's the idea. Okay, any questions? I thought there'll be at least one question here. So what are we actually doing here? We are applying clean iteration, okay? And then the only thing is there are multiple equations, and therefore you have to pick the locations to do. So I thought there will be a question that here, what is happening? You're iterating. Cleaning iteration is not really saving you anything, is it? Okay, you are ending up iterating over the loop as many times as you have. Of course, you're generating all the entire interval of values. You're not generating a single value as you would do in your while if you were to execute the program on a particular input, but you have, but you're not saving anything. If indeed the number of steps for you to propagate this interval using clean iteration takes as much time as you would as the number of times you have to kind of unwind the loop, and that could be very long. How do you, what do you, will this even scale? Okay, in practice. Okay, so that is one question. Okay, so are there ways in which you can ensure convergence faster than doing cleaning iteration one step at a time? Okay, but then there is kind of a way to do. For example, here, if there is something called, and that we will discuss maybe in the next in the next class. There is a couple of techniques called widening and narrowing, where you can extrapolate. So instead of doing enlarging the your domain at x1, one iteration, cleaning iteration at a time, if you notice that what is happening at location 1 is there is a pattern in which this is extended from 0, 0, you extend to 0, 1, then it gets extended to 0, 2, and so on and so forth. It is kind of an increasing thing. But maybe if you can define an extrapolating operator, which allows you to jump, you will see this pattern up to a certain number of iterations. After that, you will say, oh, the heck, I will extrapolate this and assume I will take a jump. Okay, and maybe this keeps on going. So I will do 0 to infinity. Okay. Of course, 0 to infinity is always a fixed point. Okay, when you extend that to infinity, it will be extrapolate that to infinity. It will be a fixed point. So when you jump it you extrapolate it to overshoot your least fixed point and then get to some over, even over, an over approximated fixed point. If you got that, then you could come back from that. Okay, then your x3 will become 1 to something like this will immediately become infinity, and then you can get adjusted. Okay, you can pull it back into to phi from that through a narrowing, the reverse of this extrapolating algorithm. So there is this idea of extrapolating to a extrapolation, and then this concept of narrowing, where you tighten your extrapolated fixed point back to get into a thing by doing this back and forth, which will be faster than doing it one iteration at a time. Okay. Okay. So that I will we will see what the idea behind such an extrapolation operation is to get faster convergence next time. Okay, on Friday. So we're already at 3:05. Is Diganta here?
Yes, sir, I'm here.
Okay, so I don't know. Sorry, as I always do, I take too much time. Is there, can you guys, let's see how many people are here. Sudakshina is here. Harsh is not. Harsh and Dhruv have left. Okay, so maybe you can do it on Thursday.
Yeah, sure, I'll do it.
So you have uploaded the thing, no?
Yeah, I have uploaded, and I think people are also starting to install them.
Yeah, I think what we should make is some tasks that they can get started on. Okay, both for reviewing it and started running. So, by the way, what I need is your, your teammate for the first task, which involves doing CBMC, this emulator verification. That's a team project, okay, with one of the person. So you have to email us the partner that you have chosen. Okay, this applies for CMI folks. For Anleep and Sudakshina, I will talk to you. I will call you later today or tomorrow. Yeah? So you have to send me send us your teammate, the rest of the four of you. So we will email you some exercise that we want you to do before next class, and Diganta will discuss, will review the code and what is expected of you on Thursday. Yeah? Okay, any questions?